Reinforcement learning, RL, enables robots to acquire complex skills, but its success hinges on effective representation learning, particularly in images. Traditional RL approaches process 2D images, neglecting the world's 3D geometric structure. Although 3D-aware representations are crucial, current methods often require calibrated cameras or multi-view setups. Our framework overcomes these challenges by deriving 3D representations from single-view RGB inputs without camera-posed data, improving downstream RL tasks. Here, we will describe the overall training framework. Let's assume we have a dataset with 6 viewpoints for pre-training NeRF. To pre-train NeRF, first, we randomly select a primary image. It is masked for cross-view completion tasks. Second, we randomly select reference images except for the viewpoint of the primary image. In this work, we select 2 viewpoints for the reference images. Then, by utilizing NeRF, we reconstruct all viewpoints except the selected 2 reference images. In this case, the number of viewpoints for reconstruction is 4. In summary, given a pair of primary image, reference images, and images for reconstruction, the 3D scene encoder takes the primary image and reference images as inputs. Then, the 3D scene encoder extracts the 3D scene representation Z, and the NeRF model takes this representation Z in addition to the position and view direction for 3D volume rendering. The NeRF model reconstructs all viewpoints in the dataset, except for the viewpoints of reference images. After training the NeRF model with the 3D scene encoder, we perform downstream RL with this learned 3D scene representation. Since we no longer use NeRF model in this stage, we only need the inference of the pre-trained 3D scene encoder. For the downstream RL process, we extract the 3D scene representation Z, and utilize this representation as observation input for the RL agent. Qualitative rendering results are shown here. We render a video of a task-solving trajectory from 6 different viewpoints only with single-view input, which is the same as the deployment setup. As you can see in the videos, our method can consistently capture the fine-grained details such as the green peg, while other baselines show failures such as teleportation of the robot or objects in the case of SNRL, NeRF RL, or jittering motions in 3D and SR. Similar phenomena are observed in the hammer environment. Our method shows stable rendering results from the grasping moment to nail-hitting moment. However, other baselines such as SNRL and NeRF RL fail to capture the accurate position of the hammer, leading to ghost moving of the hammer without being grasped by the gripper. Or, these baselines sometimes show teleportation after hitting the nail. After pre-training NeRF, we train the downstream RL agent, and the evaluation results are shown here. Our method consistently performs the given task, while other baselines mostly fail to grasp the peg or accurately insert it into the hole, even though they are trained with multi-view input. Since we use the same downstream RL algorithm for all methods, the only difference is the representation learning in the backbone encoder network, which shows its importance in downstream RL. These are RL evaluation results for the hammer environment. Our method consistently performs the given task, while other baselines mostly fail to interact with the hammer. Since the motivation of this work is reducing the number of cameras for practical applicability in the real world, we also conducted real-world experiments, using a UR3 robot. As you can see in these videos, our method successfully renders the dynamic scene, even in the unseen viewpoints. It supports that the proposed 3D scene encoder captures the essential 3D information of the environment, providing 3D-aware implicit representation. Compared to our method, all other baselines show some jittering or fail to capture fine-grained details of the environment, similar to the simulation settings. To validate the effectiveness of the learned 3D representation, we conducted real-world RL experiments. As shown in the videos, our method accurately grasps objects such as deformable towels, handle of the kettle, and bowls, and then performed the given task successfully, even though it has provided only a single-view image as input. We additionally evaluate the learned policy with viewpoint perturbation. As shown in these videos, our method can perform the given task despite the perturbation. Since these perturbed viewpoints are never seen during the NeRF pre-training, this robustness showcases the advantages of the learned implicit 3D-aware representation. Unless it is aware of 3D geometry, the representation of the perturbed viewpoint will collapse to weird values, leading to the failure of the RL policy. Similar to simulation settings, other baselines usually fail to perform the given tasks, despite using multiple viewpoints. Specifically, they show reaching behavior to the object of interest, but they often struggle to do precise manipulation such as grasping the object, which requires accurate 3D information about the object. We also evaluate the learned policy under viewpoint perturbations by altering the position of one of the stereo cameras, following a setup similar to our previous experiment on viewpoint robustness. As demonstrated in these videos, the baseline methods are sensitive to viewpoint changes, mostly resulting in failures to complete the given task.